Hello everyone. Today I just wanted to go over a topic related in material engineering in the civil materials, specifically over the maximum specific gravity for asphalt. Kind of something that gets confused about. Wanted to go over the derivation kind of on or how you can formulate it and kind of get a better understanding of it. So just to go over what specific gravity means in general. It's just the density of a substance divided by the density of water at 4 degrees, because the density of water at 4 degrees is the closest to 1 gram per cubic centimeter. So basically that's what we're going to be kind of solving for to some extent. I'm also going to be going over the maximum theoretical density and how those, how the maximum specific gravity and maximum theoretical density are different. So I'm just going to go over this formulation here. So if you look to the far left, I have an apparatus of the maximum theoretical specific gravity, if you want to call it that apparatus. But basically all you have is a scale attached to a tension rope, which is attached to a basket which holds a specimen that is completely submerged in water. So if you just kind of detach the system, draw a free body diagram, you have your tension force going upwards, you have a buoyant force acting on the specimen going upwards, and a force of gravity going downwards on this apparatus. So if you solve for the forces in the y direction, everything's static, so there's no acceleration. You can formulate that it's tension plus the buoyant force minus the gravity force, and this will all equal 0. The buoyant force is equal to the density of water at, should actually say at x degrees Celsius, not 40, because it's dependent on whatever temperature the water is at. So if this is at 25 degrees Celsius, 5 degrees Celsius, you'll need to use the density of water relative to that temperature times by the volume displaced, which is actually the volume that is displaced by the stones in the bitumen, basically. Because when you, so say you place like a steel ball in water, the water raises up. However much volume that water raised up is equivalent to the volume of the object that you put into the into the water. So given that, that's the buoyant force, and that's multiplied by gravity. The tension force is measured on the scale as the mass of asphalt in the water times gravity. And this is actually measuring the difference between the buoyant force and the gravity, essentially. But we have a measurement for it from the scale. So then we also have a measurement for the mass of asphalt in air before we submerge the specimen. So we know these two values. So then if we solve for the buoyant force by just adding over gravity and subtracting over the tension and plugging in our values, we see that gravity is going, you can factor out gravity on this side, cancel it out, and that leaves with just the density of water at whatever temperature the water bath is at, multiplied by the volume of displaced liquid from the specimen, and that's equal to the mass of asphalt in air minus the mass of asphalt in water. And we have these two values, so we can calculate this. However, this value doesn't mean much. This value means something. It means it's basically the true volume that will calculate the maximum theoretical density. It's still a like the value you're still going to get at the end of this is a theoretical density. Like you can't have zero air voids within your specimen. However, this is the true volume that will calculate the density, not specific gravity. So when you divide by the density of water at, say, 25 degrees Celsius, which is the ASTM, this is, I think, 7, I think. Could be wrong. Something around there. You get this volume, and then if you divide the mass in air, that'll be the density of the substance, basically. And so if you want to calculate the specific gravity, you would, since specific gravity is related to something that's only to the density of water at 4 degrees Celsius, you then, because that's the original specific gravity, is just density of substance divided by the density of water at 4 degrees Celsius. It's always related to basically, it's always related to 1 gram per centimeter cube. So the volume then for the specific gravity is the volume when weighed at 4 degrees Celsius water, not the volume that is obtained when you weigh it in 25 degrees Celsius water. That will obtain you the maximum theoretical density. Maximum specific gravity will then be the volume, or these two masses subtracted from each other, divided by the density of water at 4 degrees Celsius. So then that makes this just equal to the top term, because this is just 1. It doesn't change. So then the maximum specific gravity, M.S.G, is equal to the mass of asphalt in air divided by the mass of asphalt in water divided by minus mass of asphalt. Sorry, mass of asphalt in air minus the mass of asphalt in water, because this is the same. Now the maximum theoretical density is the mass of asphalt in air divided by the same thing that's here, but you're going to multiply by the density of water at whatever temperature the water bath is at. Well, the ASTM is 25 degrees, so you should be at 25 degrees Celsius. And that's because of this volume here for the density divided by that. So when you go mass divided by volume, that's going to flip back up to this is going to flip into the numerator, basically. So then you multiply instead of divide. Hopefully that makes sense and kind of clears some things up about specific gravity and theoretical density related to asphalt mixtures. Thank you.